In the previous video, we saw that rate was dependent upon the concentrations of our reactants and also upon the rate constant, which is affected by the temperature, but also by the likelihood of reactants colliding together with the proper amount of kinetic energy and the proper orientation, etc. as well. So this is related to temperature. So this K, this rate constant, changes as temperature changes, which we'll see later. And so this rate law can allow us to predict how changing the concentrations of reactants might change the rate of reaction. We can describe this rate law using the orders of each reactant and the overall order of the reaction. Given that rate is equal to K times AX, BY, X is the order of our reactant A, and Y is the order of our reactant B. And so we can say that the reaction is X order in A. So for example, if X were 1, we would say it's first order in A. And then if Y were equal to 2, we would say the reaction is second order in B. And we would say that the overall reaction is X plus Y, or 1 plus 2, third order overall. Now generally, these values, X and Y, are not equal to the coefficients in front of our reactants, A and B. Occasionally they are, but oftentimes they're not, so we can't just presume these values of X and Y. In fact, in order to know these values of X and Y, we actually have to do experiments. Yes, the order of the reactants is going to be found by changing the rates of reaction by changing the concentrations of the reactants, keeping the other reactant concentrations constant. So we'll see that by, say, doubling the concentration of one reactant, we might double the rate, implying the order of that reactant, as long as this other reactant was held constant in concentration. Or by doubling the order of a reactant and holding the other reactant's concentration constant, we can double the rate of the reaction, or quadruple, etc. Yes, changing the concentrations of these changes the rates of reaction. So, I guess I'd like to kind of establish the relationships of changing the concentrations of things, which result in a certain change in rates, as dependent upon these exponents, the orders of our reactants. So creating a hypothetical reaction where A and B and C react together to form D, we might say that the rate is equal to K times A to the first power, B to the second, C to the 0 power. So considering this scenario, and considering then that each reactant has a concentration of X, then the rate would be equal to K times X to the first power, X to the second power, and X to the 0 power. Or rate is equal to Kx cubed. So in our simplest case, rate is equal to Kx cubed. But what happens if we change the concentrations of our reactants? What happens to the rate? Well, first, consider doubling the concentration of A. So instead of regular old X here, we have 2X. What happens to the rate? Well, take that, solve this, or simplify this equation, and you'll get 2 to the first power will be involved now, and so you'll have rate is equal to K times 2X cubed. You see that by doubling the concentration of a reactant, which is to the first power, you'll double the rate of the reaction. Okay, so doubling the concentration of a reaction, which is to the first order, will double the rate of a reaction. Consider doubling the concentration of B, this reactant, which is to the second power, or second order. By doing that, you see that the rate would be equal to K times 4x cubed. This is 4 times bigger than our original simple case. We can see that by doubling the concentration of a reactant, which is to the second order, will actually quadruple the rate. Now, what if you were to triple the concentration of this second order reactant? What would happen to the rate? Well, you'll remember that to get to that 4, we took 2 and then we squared it. That gave us 4. If you were to square 3, you would get 9. So by tripling the concentration of a second order reactant, we'll actually multiply the rate of the reaction by 9. What if you were to triple the concentration of a first order reactant? What would happen to the rate? It would triple, 3 to the first power. But what if you were to double, say, the concentration of a zero order reactant? Well, that actually would not affect the rate whatsoever. It's still kx cubed. And so you can see that doubling or tripling the concentration of a zero order reactant actually has no change on the rate of reaction. And so this chart is really kind of fundamental to your solving our problems. So you'll want to memorize this. So just remember 2 to the 0 power gives 1, or no change. 2 to the first power gives, I guess, a linear change. Doubling the concentration doubles the rate. And then 2 to the second power, for a second order reaction, you'll have an exponential function. Doubling concentration quadruples rate, etc. Okay, so we can use this chart then to help determine the rate law of a certain reaction. For example, consider this reaction, 2 NOs combined with an H2. Now, in order to know the rate law, which is going to be our first objective, determine the rate law, we need to know the order of each reactant. And so we can test what happens to the rate if we change the concentration of the reactants, keeping the other reactants constant in concentration. So, what happens if we change, say, double the concentration of NO? What happens to the rate of the reaction if hydrogen is held constant? Well, you can see that doubling the concentration of NO, going from 5 times 10 to the negative 3 to 10 to the negative 3, actually makes the rate of the reaction go up about 4 times. Doubling the concentration of this reactant quadruples the rate. What is the order of A then? Doubling the concentration of a reactant quadruples the rate. That means that that reactant must be second order. So we just determined that A is second order. What is the order of B? So find experiments. One of these 3 experiments, actually 2 of these 3 experiments in which NO is held constant, and H2 is changed. Here, H2 is doubled. What happens to the rate of the reaction? Here it goes down. by 5 times? No, hold on. Actually, 1.0 times 10 to the negative 4 is 10 times 10 to the negative 5. We see that the rate went from 5 to 10 to the negative 5. It actually doubled. So holding this other reactant constant and doubling H2, we can see a doubling in the rate of the reaction. And so we know then, let's see, if they have a linear relationship like that, double one, double the other, that means we have a first order reactant. And so B must be to the first order. And then we can solve for the rate constant now using this known rate law. We can say, what is the constant in any of these different experiments? It should be the same in all of them because it's a rate constant. So plug in for any of these. For example, you could plug in this, this, and that, as long as they're all in the same experiment. And you might find then that the rate, which was 1.3 times 10 to the negative 5 in this case, and then divide by the concentration of A, which was, let's see, 5.0 times 10 to the negative 3, and then squared times 2.0 times 10 to the negative 3 to the first power. That should give us then that the rate constant is 260. And what unit is that? Let's see, rate was in molar per second, and then divide by molar times molar, because it's squared, and then times molar again. So that's a molar squared over a molar cubed. That should give us 1 over molar squared second. And then you can solve for the rate of the reaction given these different concentrations. So plug in then this now known rate constant, 260, reciprocal molar seconds, molar square seconds, and you should find that the rate is equal to 2.2 times 10 to the negative 4. Thanks for watching.